We will hear an interesting presentation by Tiffany Cachet this morning on his dissertation thesis. And I was fascinated to see that there are 3 different research units from which you are getting your degree, from biology, from chemistry, and also Max Planck Institute, of course. So this demonstrates the wide use and importance of nitrogen in the Earth system. So you have 30 minutes for your presentation, and after that we will have questions to you.
Thank you.
Go ahead.
So thank you very much for coming to my PhD defense. My PhD thesis topic is species-specific nitrogen isotope analysis and nanosieves. First, this is an overview of this presentation. This is the overview of this presentation. Firstly, I will give you a short introduction. Then I will show the analytical technique. In the third part, I will show the experiments and the results about this work. In the end, I will give the summary. First, introduction. The global reactive nitrogen cycle. The global reactive nitrogen cycle plays a central role in sustaining life on Earth. Moreover, it plays a key role in certain environmental problems. It controls tropospheric ozone formation. It leads to the formation of secondary aerosols. Both ozone and aerosols contribute to global climate change, air pollution, and human health. Long-range transport of reactive nitrogen influences global carbon cycle. You can see it is very important to understand reactive nitrogen in several reasons. Nitrogen isotope ratio can help us understand this better. It is a ratio of abundances of 50 nitrogen over 40 nitrogen. In the environment, this ratio is a very small number. Usually, we use standard compared to sample to calculate nitrogen this ratio in per mole scale. Because the average abundance of 50 nitrogen in the air is very constant, so we use air as the standard to calculate 50 nitrogen. For example, minus 10 per mole, which means in the sample it has 10 per mole less 50 nitrogen than the air. Similarly, if this number is positive, which means our sample enriched in 50 nitrogen. Stable nitrogen isotope ratios can help us to trace atmospheric aerosol sources, processes, and transport. However, if we do this, we need the right analytical tools. Many conventional nitrogen isotope analysis techniques require large bulk aerosol particle samples and provide the isotope ratio of total nitrogen as one single value measurement. In the environment, reactive nitrogen includes contribution from nitrate, ammonium, and organic reactive nitrogen. All these species have different sources and are cycled via different reaction pathways. Different sources of reactive nitrogen are frequently found internally mixed in the same particle. This image shows previous work. From this image, we can see inorganic salts are coated by organic compounds. So we need a tool that they can separate different nitrogen-bearing species for nitrate, ammonium, or organic reactive nitrogen, and measure species-specific nitrogen isotope ratio in single particle level. So the goal of this thesis is first separate different species in the nanosieves, and then measure species-specific nitrogen isotope ratio. And more important, this measurement should be done in single particle level for submicron or micrometer scale. Throughout this work, I use international isotopic standards and in-house standards. All experiments do in the lab, and no real ambient aerosol so far analyzed. Analytical technique. This is the tool used in this work, SIMS. When a solid sample are spotted by primary ions with few kilo electron voltage energy, a fraction of particles emitted from the target. these particles is ionized. Second ion mass spectrometry measures these second ions with a mass spectrometer. The second ion emission by a solid surface under ion bombardment provides the information about this elemental, isotopic, and molecular composition of its uppermost atomic layers. SIMS are recognized as the most sensitive surface, elemental and isotopic surface analysis technique. This is the instrument used in this work, NanoSIMS 50. It has two primary ion sources, oxygen minus and phases plus. Primary ions are focused on the sample surface with high lateral resolution down to 50 nanometers for phases plus primary ions and 200 to 300 nanometers for oxygen minus primary ions. Samples are spotted by primary ions, and secondary ions are extracted, transmitted, and detected in mass spectrometer with high detection efficiency and high mass resolution. 5 different masses can be measured simultaneously. These features permit to analyze natural isotopic composition containing aerosols in micrometer and submicrometer scale. Here I'll give you an example from the real aerosol sample from Amazon rainforest, which measured in nanosims and SEM. First, negative second ion images are produced by phases plus primary ions. Second row, positive second ion images are produced by oxygen minus primary ions. These SEM images are obtained in the same scanning area after nanosims analysis. From this image, we can see fungal hyphae and salt particles. For example, these two particles contain sodium and one of them contains nitrate. From the scale, we can see this sodium nitrate particle is approximately 1 micrometer in diameter. So I try to develop a method measure natural isotopic composition in such particles. The experiments and the results, I separate my results in this 4 parts. I will show more details in the next 2 minutes. First, I will show the sample preparation, including pressed bulk pressed samples and aerosol-like mixture samples. In the second part, I will use positive second ions and negative second ions measure to classify different nitrogen-bearing species. Measure natural isotope ratios using nanosims. The challenges most come from the instrument mass fractionation. It results our measured isotope ratios different from the true value in the sample. Usually, we use known isotopic composition standard measure in this instrument to study the instrument mass fractionation, which is calculated by dirt 15 nitrogen bias using this equation. So, the instrument mass fractionation occurs in several stages during nanosims analysis. It includes primary ion beam sputtering, secondary ions, ionization, extraction, transmission, and detection. For the sputtering and ionization in this work, firstly, I investigated the measurement conditions, including size of scanning fields, pre-sparking time, primary ion dose, and measurement time. More important, I investigated the metric effect, which is produced by different cations, for example, potassium nitrate and sodium nitrate. This will be shown in the third part. And I also measure aerosol-like mixture samples with the presence of carbon in the first part. Other stages, like secondary ions extraction, transmission, and detection, the instrument mass fractionation effect is relatively stable. So first, sample preparation. I use international isotopic standards and inorganic and organic in-house standards. Bulk samples are pressed on ultra-clean gold foil with gold coating, then measured in nanosims. Most of those standards are successfully measured except calcium nitrate and ammonium nitrate. The reason is for calcium nitrate is activates in laboratory conditions, then become a droplet, which makes our sample preparation challenging, and also a challenge for nanosims analysis. For ammonium nitrate, it's unstable in high vacuum conditions, which we cannot measure these materials in the nanosims. Aerosol-like mixture samples are generated from nitrate with glucose solutions using these equipment. We use these standards to study the metric effect instrument mass fractionation with the presence of carbon, which can form high C minus second ion ratio, second ions. And we also use this sample to simulate atmospheric aerosol conditions. Samples are collected on gold-coated nuclear filters, silver filters, silicon wafers, and gold foils. The gold-coated nuclear filters are successfully used in this work, and it also successfully used in soft aerosol analysis in nanosins previously. For silver filters, it has good electronic conductivity but bad surface. It is not flat enough for nanosins analysis. Silicon wafers and gold foils have good electronic conductivity and flat enough. In the second part, the separation of different nitrogen-bearing species in the nanosins, I found that negative second ion emissions from sodium nitrate and sodium nitrite, compared to different negative second ions, we found that this species shows the highest NO2 minus second ion molecular ion yield. So we compare this high signal to other species. We found that other species don't show this high signal. It's especially for urea, cysteine, and ammonium sulfate. All of these molecules both contain nitrogen and oxygen atoms, but they do not form NO2 minus second ions. So this means NO2 minus second ions are unique for nitrate and nitrite species. Positive second ion emissions from ammonium sulfate, urea, and cysteine compared to different positive second ions, the result shows that they have the highest NH4 plus second ions. We notice that for urea and cysteine, these two molecules only contain NO2 groups, but they still shows the highest NH4 plus second ions. This means this second ion can be formed during sputtering process in the nanosins analysis. Similarly, we compare this high signal with other different species. We found that other species don't show